Heidi-ho, Renaissanceteers, and welcome to our 100th Renaissance quiz. A noteworthy occasion like this certainly deserves a video, and so today I would like to speak to you about a matter of gravity. Did you know that you weigh more at the North Pole than you do at the equator? It's true. A 200-pound Eskimo living at the North Pole would only weigh about 199 pounds at the equator. There are two reasons for this.
One reason that we weigh less at the equator is because the Earth is rotating. And like children on a merry-go-round, the ones on the outer rim or equator are being hurled outwards by centrifugal force, effectively counteracting gravity, while those close to the center, or North Pole, feel very little centrifugal force. We derived the formula for centrifugal force in Renaissance quiz number 58. I will leave it up to you to check my calculation, but the weight reduction due to centrifugal force at the equator is about 0.3%, or about 0.6 pounds for a 200-pound Eskimo. So what causes the remainder of the 1-pound weight reduction? The second reason for the weight reduction at the equator is due to Earth's shape. The Earth is not a perfect sphere. It bulges at the equator slightly. The bulge is not very noticeable, but the Earth measures 12,713 kilometers from North Pole to South Pole, and about 0.3% more, or 12,756 kilometers thickness at the equator. Search Wikipedia for gravity of Earth, and you will find the following statement. This equatorial bulge causes objects at the equator to be farther from the planet's center than objects at the poles, because the force due to gravitational attraction between two bodies varies inversely with the square of the distance between them. An object at the equator experiences a weaker gravitational pull than an object at the poles. This explanation in Wikipedia bothers me. I believe it is incorrect, or at best is only a partial truth. Suppose we hire the Intergalactic Planetary Excavation Company, IGPEC, to bore a hole through the center of the Earth. Here comes the IGPEC flying saucer, turns on its powerful laser beam, and bores a hole through the Earth. Then we call on our old friend Pegman. You've seen Pegman before. He's a little figure on Google Maps. You use him to find the street view. Let's position Pegman right beside our giant hole. So let's give Pegman a little nudge and see what happens. Oh no, Mr. Bill! Pegman falls through the center of the Earth and keeps on going and oscillates up and down till he finally comes to rest in the center of the Earth, where he is totally weightless. This is because all the mass of the Earth is pulling him in different directions, and it all cancels out with a net gravitational force of 0. So the notion that being closer to the center of the Earth increases your weight obviously is not always true. But wait, you say. Newton's law of universal gravitation applies to point masses that are separate from each other. It does not apply to large volume masses when one mass is inside the other. This is true, but point masses are just a convenient mathematical concept. When was the last time you saw a mass that had 0 volume? Newton showed that a uniform spherical mass behaves like a point mass when you are outside of the sphere. However, this useful simplification only applies to spheres, not to oblate volumes like our flattened Earth. To show this more clearly, let's exaggerate the flatness of the Earth so that it looks more like the shape of an M&M candy piece, and imagine Pegman standing at the North Pole. Rather than a point mass, the Earth is made up of many tiny pieces of mass bonded together. Each little piece of the Earth is exerting a gravitational pull on Pegman, but the pieces near the equator on opposite sides are symmetrically pulling at angles that are nearly opposed to each other. The result is that much of the gravitational force from these peripheral pieces cancel out, leaving a smaller net force on Pegman. Now let's look at Pegman standing on the equator of this exaggeratedly flattened Earth. Although Pegman is now further away from the center of the Earth, you can see that the gravitational pull of the peripheral parts of the Earth are closer to being in line with each other, and therefore their net gravitational pull is greater. So if we ignore Earth's rotation for a moment and consider it to be a uniform oblate spheroid, where would Pegman weigh more, on the equator or at the poles? If you are good at vector calculus, you could integrate the gravitational force of each incremental volume of the oblate spheroid over its entire volume to come up with the net gravitational force on a point mass at its surface. Perhaps one of our luminary mathematical Renaissanceteers is up to the task, but I am not good at vector calculus. Maybe there is a simpler way to get to the answer. Here's where you come in to work on the Renaissance puzzle.
The American psychologist Abraham Maslow once said, "If the only tool you have is a hammer, then it is tempting to treat everything as if it were a nail." This rule is known as Maslow's golden hammer, which is not to be confused with Maxwell's silver hammer. Well, I am guilty as charged, and since the only object I know how to deal with is a sphere, I tend to think of everything as clusters of spheres. So here we have our flattened sphere modeled as 7 individual spheres bonded together. In this case, the individual spheres are, of course, tennis balls. Now, the question is, would our Pegman weigh more if he were sitting on the center sphere like this, or would he weigh more if he were sitting on a peripheral sphere like this?
To answer this question, you need to know Newton's law of universal gravitation, which says that the force of attraction between two spherical masses is equal to the product of the two masses times the gravitational constant divided by the square of the distance between them. Since we are looking only to find the relative magnitude of the gravitational attraction from two different locations on this cluster of spheres, we do not need to know the mass of the spheres or the mass of Pegman. Furthermore, consider Pegman to be tinier than a microbe on the surface of the tennis balls, so that you do not need to worry about his dimensions. Just think of him as a point mass.
And so, Renaissanceteers, I hope you find this puzzle an interesting challenge, and the only thing you need to solve it is the knowledge of Newton's law of gravitation, which is given in the presentation, and a little bit of trigonometry. Very simple stuff. So, I hope you'll give it a shot, and best of luck.